Our third speaker, and this is a change to the original program. Unfortunately, Dr. Castellanza from the University of Milan was unable to be here today, but thankfully we have a close colleague, Dr. Federico Pisanò, who's worked very closely with Dr. Castellanza. Federico has obtained his PhD from Milan back in 2011, and he has also travelled, spent some time at Davis and also in Madrid. His subject matter, and we'll come to the title later, his subject matter is very topical in terms of what we're trying to show you today with solid structure interaction and numerical.
So in the next few minutes I will be giving a short overview about the use of macroelement modeling in combination with finite element models for the analysis of dynamics of structure interaction. So a brief overview. After introducing some preliminary concepts about structure interaction, I will go through the main idea at the base of the macroelement modeling, and especially about how necessary it is in real application to combine both the approach, finite element and macroelement modeling, for solving real problems. And then after going through some application example, we draw some conclusion, and especially the future perspective along this line of research and application. So, as is well known, dynamics of structure interaction phenomena may be responsible in many cases for considerable economic and human losses. And in this slide, I'm just reporting a few examples from damages occurring at foundations and retaining structure from earthquakes in the last 50 years. So just from these few pictures, it is apparent how important it is still nowadays to keep doing research and application on this topic, to design and make our structure safer and more resilient to earthquake events. So let's first give a basic schematization of the phenomenon. So seismic events, very basically, can be described like the path of seismic waves from a source placed at some deep location within the earth crust to the anthropized surface where our structures are usually located. During this path, seismic waves cross several portions of the earth crust, passing from the so-called far field, where the location and the existence of the superstructures is basically uninfluential, up to get the so-called near field, where instead the existence of the structure has some influence on the seismic event itself. From the point of view of seismic interaction, we call actually interaction the fact that during the motion, the structure and the earth motion basically influence each other. And this is very important from the point of view of designing the structures. Okay, so if you want to really go through numerical modeling of this kind of phenomena, nowadays we have the capability of conceiving a quite sophisticated numerical model, taking into account at the same time the presence of the seismic force, of complex stratigraphy, and even complex topography. For instance, you can see here an example coming from 2004 by a colleague of mine at Politecnico di Milano, in which a fully 3D modeling of an ancient Roman bridge in Italy has been done through a finite element simulation. And of course, nowadays we have all the theoretical and potential numerical capability to do this, but things might be not that easy if we are in the case with a strong nonlinearity, because as you well know, the fact that we might want to take into account a nonlinear phenomenon occurring in proximity of the structure would make our numerical analysis more and more cumbersome from a computational point of view. So this is in principle feasible, but in some cases not really. And in particular, if you want to get some reliable modeling of this kind of dynamics of structure interaction phenomena, we gotta make sure that we have at least a 3D model in which we are able to describe the interaction of seismic waves, which can be of two types, namely bulk waves and subwave waves. neglecting one of them might be not on the safe side from the point of view of structural design. And going into much detail for soil-like materials, we also need to make sure that in nonlinear analysis we need to provide at least a decent modeling of what happens at the near field soil close to the structure, and especially at the interface. The interface behavior is always something very, very important to the structural engineer. In this context, we also should never forget that in the subsoil, we in most cases have to deal with the presence of some kind of fluid phase, which could give rise to important buoyancy effects and also to dramatic catastrophes such as the well-known phenomenon of cyclic liquefaction, which is of course an issue to be taken into account when we are dealing with some kind of interaction with the seismic events. However, as I already said, setting up a model able to take into account the seismic source, wave propagation, and the high nonlinearities occurring in the interface between structure and soils might be not easy task. So at this point, a simplified idea comes out, and this is actually the idea of trying to do some kind of uncoupling between what happens at the far field level and the near field level. In particular, far field could be ideally treated in a more simplified way, in the sense that we just need to know how seismic waves propagate up to the surface, and this in many cases might be quite accurately by means of simplified approach like elastic analytical solution or even elastic numerical analysis. This would come up with a reliable estimation of the seismic motion to be used for a more in-detail analysis of what happens at the near field level. So at this point, what I'm going to say the following is basically how we do model of the interaction between the structure and the near field, which is actually characterized by usually a strongly nonlinear behavior. In doing this, we would like to couple the behavior of the structure with the behavior of another element, which henceforth we will call a macroelement, which is an element in which we lump the nonlinear behavior taking place at the foundation level and the surrounding soil. So this is the main idea. So I have here a sketch of what I'm talking about, and here there is a simplified picture of a structure already discretized according to a mass lumping approach. And we have here the very close near field soil. You can see here the standard equation of motion we use usually for our structural dynamic analysis. And I took care of putting into explicit account a separation between the degrees of freedom belonging to the structure and the degrees of freedom belonging to the foundation, which I refer with the letter F. See? So at this point, we are trying to provide a distinct modeling of the superstructure and the soil foundation system. And from the point of view of numerical analysis, these imply to be the ability of providing mass, stiffness, damping and stiffness matrices upon the knowledge of the input motion, which, as I already said, comes from the far field analysis. So this is the situation. In particular, the role of the damping matrix here, CFF, is not only to describe the possible viscous damping occurring at the soil level, but also to take into account the fact that while we are dynamically excitating a structure, there is always some kind of geometrical spreading of surface waves. This is called usually radiation damping. So this might be a trick, I would say, to take into account the fact that we have a whole structure here, geological structure in which waves keeps propagating and keeps to go away from the structure. But the very core of the approach is what I symbolized here as the foundation stiffness, the KFF. So going into much detail, I can give you here a more direct representation of what KFF is. It is basically a sort of stiffness matrix, and actually it is a stiffness matrix, relating the response between some kind of generalized static variables and some kind of generalized kinematic variables. You see here the representation of a very simple foundation, like a strip footing, in which what is called the static variable are basically the forces acting on the structure. You have here the vertical force, the moment force, and the horizontal force. In a 3D context, you usually have 60 degrees of freedom, so with torques and the force into direction and bending moments into direction. About some kind of work conjugate process, you also are able to identify the corresponding kinematic variables, which are, of course, in the context of the foundation kinematic, are displacement and rotation. What is in between them is actually the stiffness matrix KFFF, which is the representation of the so-called macroelement modeling. So, from this point of view, the macroelement is nothing but a constitutive relationship which is not defined in terms of local soil behavior, but in terms of soil foundation behavior. It's like an upscaling process in which we try to describe with a single element what is actually taking place at a more complex level. It is also important to notice that in the most general case, we cannot assume any simplifying assumption of how to form this matrix, because we always need to recognize that the relationship between forces and displacement needs to be full, in the sense that it's not diagonal, and in general not symmetric, which is easily understandable, because if you are thinking about elasticity, we all know that under a vertical load you usually don't obtain any rotation or any horizontal displacement. But experimental evidences tell us that it is not the case, because under, for instance, horizontal seismic shaking, we usually have settlements. And this is the very clear appearance of the fact that these metrics need to be full in general. Okay? So, the idea is set, we know what we want to do. The question is how. So, we wanted to establish a constitutive relationship for the behavior of the foundation. So, what would be the framework for doing that? Since we are pretty confident with this kind of problems when we are talking about constitutive modeling of soil behavior, the idea is to keep pretty much the same when we are talking about this macro element behavior. And what is usually done is developing the constitutive relationship between static and kinematic variables in the framework of strain handling elastoplasticity. So this doesn't introduce any new modeling concept, but it's just the use which is different with respect to what we usually do. So if we want to really define a constitutive relationship, we need to provide the analysis facility with all the ingredients that an elastoplastic model requires, which are mainly an elastic flow, the definition of a nil function, and then eventually of a failure locus, the definition of the plastic rule in combination with the plastic potential, and of course harmony rules. The very important observation to be made at this point is the fact that once we have the constitutive relationship, whatever it is, we need to calibrate constitutive parameters. But in this case, constitutive parameters do not come exclusively from soil parameters, but are always a mutual combination of soil and geometrical parameters of the foundation. If you, even as a simplifying example, if you think to elastic formulas for computing foundation settlements, you always have in the formula the Young modulus and the Poisson ratio, but also the size of the foundation. So it's never a relationship between force and displacement only in terms of soil parameters. You always need the geometry of the foundation, which can be easy, can be complex, can be many things depending on the application. Okay. So, I already said in this slide what are the general ingredients for our models. Now, I just spent a few minutes to give you an idea on how we can obtain them. Okay? So, the first ingredient I would like to introduce is the way in which we obtain the so-called failure locus, which can also be called the interaction domain. The failure locus, from a conceptual point of view, is basically a geometrical locus in the force spaces defining the loading combination leading the foundation to failure. So basically we have a representation in which you see here that any point on the surface give you values of horizontal, vertical, and moment action on the foundation, which lead the foundation to actual collapse. Okay? And regardless of the kind of application we are trying to do, which can be displacement-based or just static-based, this kind of information is very important to practical purposes because it gives you a visual representation on how your current state, depending on your current situation, the structure, is far from the foundational collapse. And these situations can be very different depending on the kind of structure we are talking about. For instance, we have here the two pictures regarding a very modern building or an historical building here in Italy. And you can see here, like, depending on the standard codes that in history we have been complaining with, we have been dealing with, you can have an initial point which can be on this side or on the other side close to failure, depending on how much safety the designer took at the moment of designing the foundation. So the issue related to obtain this kind of locus is that it can hardly be obtained analytical. Of course, we are able today to use analytical solutions for estimating the bearing capacity of a steel foundation on a flat surface soil. But just imagine that your topography is more complex, or you have stratigraphic variability under the depth. So in that case, we already know that standard formula from geotechnical engineering cannot be employed to obtain a locus like this. So something else is needed, and in particular, you can already imagine that finite element modeling will give us some help from this point of view. I will talk about this later. Then, the other ingredients I mentioned are, of course, the elastic locus, so the geometrical locus inside which the behavior of the foundation can be assumed to be elastic, and the hardening rules describing the behavior of the foundation up to failure. At variance with what is usually assumed with standard soil modeling, if we are talking about a complex system like this might be, we can never identify a real elastic domain. Because just think about this process. There is the vertical loading of a steel foundation. You load the foundation, and no matter how low is your load, you immediately find plastification at the corners of the foundation. So if you take a look at the load settlement responses you obtain from finite element analysis, you can never say that this initial branch is elastic because it already stems from some plastification within the systems. So when we are trying to design the constitutive model for the soil foundation system, we need at the very first moment to conceive a combination between the elastic response and the hardening rules. We need to match what we obtain from possible experimental results, we might have them, or in most cases from numerical analysis. So, okay, we decided that to follow this approach we need a constitutive relationship, but an important question needs to be answered. So, how much complex, how much difficult needs to be this constitutive relationship? So, which kind of experimental results we need to cope with? I'm giving here just a couple of examples. You see here the results of small-scale tests performed on a square foundation loaded by cyclic eccentric load. So basically we have moments alternatively changing on the foundation. And just take a look at the moment rotational response you obtain from experiments. Apparently the response is nonlinear because we don't follow a straight line. Is irreversible because upon unloading we do not recover all the deformation. But there is also another effect that we don't usually observe in soils. During your unloading path, you see here like the stiffness is here smaller and then gradually increases. And this has nothing to do with the behavior of the soil, but actually with the structural behavior of the foundation that during rocking undergoes the so-called phenomenon of uplift. Uplift is basically the detachment of the foundation with respect to the soil surfaces. And so, it is very easy to understand that while you are still in the detached configuration, even if you are unloading back the foundation, it takes some time to get again the contact with the soil. And it is actually the transition from this lower stiffness to this higher stiffness. Okay? Another important aspect of the experimental response, which I already mentioned, is the fact that even if I'm applying a substantially eccentric loading, so I'm applying moments, I see here that during time I accumulate irreversible not only rotation, but also vertical settlements. And this is why, as I mentioned before, we need to set up a constitutive relationship which is full, because we need to account for coupling between different components of loading. Okay? The situation doesn't change if we pass it to another kind of structural foundation. For instance, here I'm passing from a shallow foundation to a pile raft. So what we see here is a sketch from some kind of very recent experimental results obtained at my university, in which you see here how the pile raft responds to cyclic horizontal loads. So I'm talking here about inclined loads, actually. And what you see here again is that you have a highly nonlinear response with a high irreversibility, and you have, even in this case, an accumulation of vertical segment as the number of cycles increase, which is again an effect of coupling between the horizontal and vertical loading. And you have an interesting effect here, testified by the fact that upon unloading you cross these spaces in which the stiffness of the system is very low. And this again comes not from the behavior of the soil, but from the fact that if you think of the pile structure into the soil, when you are applying horizontal motion, you always obtain a situation in which there is some kind of detachment. And of course, until you don't get again the full connection between the soil and the pile, you always will go through this point in the response in which we have a very flat branch. So, a lesson we get from this kind of experimental results is that if we want to perform, if we want to conceive a constitutive relationship for soil foundation systems, we need some kind of more advanced modeling strategies, because at the macroelement level we don't need just to describe the soil behavior, but also that kind of geometrical nonlinearities occurring at the structural level. And we wanted to lump them into a single constitutive level for our soil foundation system. So, no matter how complicated is the soil behavior, the behavior of the soil foundation system is usually a bit more complicated from the point of view of constitutive modeling, just a little bit. But this is probably a price worth to be paid, because if on this side we are spending more efforts to model, we are saving on the other side a lot of computational time, because if we come up with some kind of relationship like this, we are not solving a problem in which we have the structure and the whole earth crust, but we are basically adding like a few degrees of freedom to my analysis, like 5, 6, no more, which is appealing. So coming back to, okay. So now in the next slides, I will go through the combination of macroelement and finite element approaches, in the sense that we usually would like to use the numerical tool like finite element programming to support the conception of macroelement modeling, mostly because we usually don't have experimental results, at least for real buildings. We usually may obtain small-scale test results, but not usually on real buildings. So finite element might give us a help on this point. Okay. So a first example, we wanna obtain the first ingredient of the macroelement model, which might be the yielding point, not even the failure, but just the yielding point. My example here comes from the ongoing realization of the third cable steel bridge on the Bosphorus, which is a pretty nice bridge in which the towers rest on the shaft foundation excavated into the bedrock under the sea. And regardless of the kind of material that we have a situation which is pretty complicated because of the topography, as you can see here. So we are already out of the simplifying assumption that we usually use for our limit analysis of foundation, because in this case there is no way we can use standard formulas for this. So we have a really complex 3D geometry. So how would we deal with that without finite elements? Okay. So all the information available on that case test regarding the material behavior and the presence of shear discontinuities under the bridge foundation were exploited to develop a finite element model in which you can see here the presence of surface loads, the presence of shear discontinuities, and here there is a zoom of the shaft foundation. The material model employed for simulating the behavior of the foundation is a very simple elastopermeable plastic model of the Hooker-Brown kind, because we are dealing with a rocky subgrade, so more Coulomb wouldn't be really appropriate because we have a curvature of the failure envelope. Going further, the idea to exploit it to obtain the necessary yielding domain is to subject the foundation to a set of combined loading tests in which we can apply a vertical load and then passing through moment excitation or horizontal excitation. What we obtain after this analysis are curves like this, in which we can observe a first fairly linear range, out of which the behavior of the structure starts to become very nonlinear. So, if for any analysis of this kind we identify visually the yielding point, then we are able to build diagrams like this, the so-called interaction domains, in which you have points coming from numerical analysis and give you in the moment vertical load plane or in the moment vertical load plane the actual shape of the yielding domain. So we know that as long as we are inside here, the load combination coming from the structure wouldn't introduce a substantial plasticity or nonlinearity in the foundational response. Anytime we are outside, we probably shouldn't rely on the inelastic approach for the analysis of the foundation. So the procedure you could implement to study, to analyze the foundation we are dealing with would be three-steps, in the sense that from a previous structural analysis we can define a sort of diagram with the ultimate real state load combination. So what do we expect that the foundation will need to sustain? Okay. Then we have the complementary finite element analysis giving us points for the load combination leading the foundation out of the elastic domain. These points may give you the inspiration to track an analytical domain which can be used for a faster verification, because we don't need to perform thousands of finite element analysis, because the yielding domain for foundation of that kind are usually shaped like this. After we have the domain, we actually do the analysis by comparing the load combination coming from the structure with the elastic domain we already said. And so at this point of the analysis we can say, okay, we are inside or we are outside of my domain, so I'm okay or I'm not. So at this point the use of the Macroelement approach is just used in a statical view, in the sense that I'm not doing here any dynamics, but I'm already at the first step of analysis. Going further into the approach, I can use the Macroelement approach to perform a quasi-static displacement belt analysis, the so-called pushover analysis, which are very much widespread in the seismic engineering community. So I'll give you here an example of what we carried out at the University. We have here to study an ancient bell tower placed in Italy, in the city of Modena. Looking at the foundation of the tower, we have the particularity that the foundation is shallow, but not really, in the sense that, as usually happens for ancient buildings, we have a pretty significant embedment of the foundation. And this has a pretty apparent consequence on the shape of the failure globus of our foundation. Basically because we have the shear interaction with the surrounding soil at this level. And it's very important for the analysis of tower buildings like this to be able to realistically describe the behavior of the foundation under moment and horizontal loads, because just think about seismic excitations or even wind excitation. Our structure, under a substantially constant vertical load, is loaded by variable horizontal action, transmitting to the foundation both horizontal and moment loads. Okay, so to study this problem, we first used the in situ data about the characterization of the soil we had to deal with, which was actually a very clay soil. So, two consequences from this observation. Dynamic analysis need to be performed in the undrained range, because we cannot count on the draining capability of a very soft soil. Also, because of the complex geological history of the deposit we were dealing with, we couldn't assume a constant distribution of the undrained shear strength of the soil. So what we did was to use finite element simulation to build a model for the foundation, the embedded foundation, and to include the spatial variability of the undrained strength, just to be as realistic as possible. After developing the Constitutive, the Finite Element model, we were able to perform different kind of Finite Element analysis, which led us to